Okay, so welcome everybody today to this DS lecture. So I have the pleasure of introducing Benjamin Jäger today. So he's of course a DS fellow here at DS, but for those of you who don't know him or so much about him maybe, I can tell you that he was a Helmholtz fellow at the Helmholtz Institute where he obtained his PhD in 2013. And then he's gone on to have various prestigious postdocs, namely in Swansea and at the ETH in Zurich, but has then ended at an even more prestigious institution, namely DS, at Nevada and CP3. So Benjamin really focuses on many things, but I can mention lattice gates theory, high performance computing, and hadron structures and form factors, anomalies, magnetic moments G-2, symmetries of finite temperatures, and sine problems and complex Langevin simulations. So I shan't keep you much more, but I just want to share a very short little story that my friend Cliff Taubes at Harvard explained at some talk. Namely, he had a student who had perfect relations to science. So if anybody's worked with science, it is very, very difficult, and you keep making mistakes. And so this student also made mistakes, and so he would submit something to Cliff Taubes. Cliff Taubes would check it, find a mistake, but he had perfect sign anomaly with Cliff Taubes because as soon as Cliff Taubes found one sign mistake, he found another. So they canceled each other, and so on they went. And eventually, I think he succeeded. So let's see how Benjamin does. The title is The Strong Forces Under Extreme Conditions. Please.
Thank you very much, Terry. Well, today in this year's talk, I will talk about, as Johan was mentioning already, the strong force under extreme conditions. And since this is a general audience talk, I will spend most of my time talking about what the title actually means and how this relates to my actual research, which I'm doing. Because I'll spend probably the last 5 to 10 minutes talking actually about results at the end. And also they will relate to the sine problem, which we just heard of. So I think a good start is to hand over to Quantum Kate to give you an idea of what all the topics are about. I have 2 videos, and one of them is, okay, what are atoms made of, in order to understand where the strong force actually plays a role.
Hi everybody, and welcome to this video! What? I'm super excited. Check out my hand, mega shaky. It's like every quark or proton or gluon inside me is shivering. No, calm down, Kate. You guys know what an atom is made of? No, right? An atom basically consists of electrons that zip around a nucleus, which is made of protons.
Hi there.
And neutrons.
What up?
But there's more.
Hey.
If you look inside neutrons or protons, you can see that they're made of even smaller parts, quarks. There are 3 in a proton, up, up, and down.
That is what we're called.
There are also gluons that carry a force called the strong force, which holds the quarks together so they don't escape. Gluons, just like glue. Glue, get it? All this is just a super small part of what we know about atoms. And there are still tons of new things to discover. Oh man, I'm totally not shivering anymore. You go, girl! Thanks for watching. It was awesome. Please subscribe. Bye-bye.
Having a brief introduction, probably stealing all the show from my talk now, but well, we'll focus about the strong force, as you already seen. Like, this is the small part here when we talk about the quarks that are inside a proton or neutron, which are then inside the atomic nucleus, which then are inside in atoms. And this is where I stop, because then we go over to chemistry, where we have the interaction between atoms and there. But when we talk about this, we need to understand what governs these. So these quarks, they have electric charge, colored charge, and they behave under the forces. So we have in physics or in science, we know of 4 fundamental forces. And the main ones are like gravity, which is probably the most common one we know about because we feel it right now, the Earth pulling us to the ground. But actually it turns out to be the weakest of all of them. It only becomes very strong because it has an unlimited range and it always is attractive. So if you put mass together, it will be more attractive, more mass will be more and more. And this force purely couples to masses of particles or like objects. This is why we can have all the galaxies, they're all attracted, and these are round. When we talk about the other 3 forces, and these are more the forces which are not that common. The next one is probably also common, is electromagnetism. And this couples to electric charge. Compared to gravity, which only couples to mass and is always attractive, electromagnetism actually has a positive charge and a negative charge. So you can combine them and have something neutral in the end. And also it means we can have something positive and positive repel each other versus positive and negatives attract each other. And this is like why electromagnetism works differently. But this is the reason, because I feel gravity pulling me towards the ground, why I'm not going into the ground, because the electric force actually of the atoms is pulling against this and prohibiting going into the inner core. So, which already implies that the electromagnetic force is stronger than the gravity, because otherwise I would fall down rather than staying where I am. Less familiar are two additional forces, which is the strong and weak force. And these are the ones that basically, you heard already Kate explaining it, the strong force couples to what we call color charge. So because we have three different types of charges, instead of just having plus and minus, we have now red, green, and blue. And these are not really the colors of these objects, but like this is a concept of trying to understand that we have three different types of charges that we can combine into something which we then call white. So we have some ways of making a neutral object again. When we had before, with positive and negatives, we could bind to zero charge. But with colors, it's a bit more complicated. We have three different types. So in order to combine those, we need to have one of each, red, green, and blue. And the strong force also is like what we know as short range. That's why it's typically also sometimes known as the strong nuclear force, because it only affects the inner part of atoms, really. The name already is a hint that meaning, okay, it's a strong force, meaning compared to the weak force, which is something which is significantly weaker. And this couples to the weak charge. Unfortunately, this is a slightly more complicated topic, which I will not go into detail, so I'll just mention here the weak charge, but this is a concept similar to the other charges, like mass, electric charge, color. It's also short-ranged, but this is mostly responsible for the radioactive decays of atoms, or nuclei. This is probably where you might have heard about this when we know that if you have a neutron in free space, it will eventually, typically after 11 minutes, decay spontaneously into a proton, an electron, and we need an anti-electron neutrino to make this. This is the process shown here in the right corner. And this is just a radioactive decay, which then mediates the weak force. So we have four forces in total. And if we think about the relative strengths, and I'm here interested at the relative strengths at very, very short distances, at 10 to the minus 50 meter or femtometer, then we say roughly the strong force is, say, order 1, and then we can compute the others in relation, and meaning electromagnetic force is 10 to the minus 2, so 1%. The weak force is 10 to the minus 6, so 0.00001. And when we talk about gravity at this scale, it's 10 to the minus 45. So meaning 0 and 45 zeros, and then a 1. So in this scale, gravity is irrelevant to all practical purposes. But it turns out if you go to some very small things, which are very, very dense in objects, or black holes, then it becomes relevant again, because then you have so much mass that compensates for the strength here. And this is where this becomes relevant. But I will focus here on what we call the strong force, because this is something my research is evolving around, and I want to explain, okay, how we put this strong force under extreme conditions. Maybe just mentioning further is like, we have the standard model of particle physics, which is explaining how all the matter and all the forces interact with each other. You see, I left out gravity because we currently don't have an understanding of quantum theory of gravity. We have Einstein's equations of motion, and these work very well, but unfortunately, when we try to combine this with a quantum theory, this does not work out, or people have not found a consistent way. There's, of course, attempts like superstring theory or various other things like quantum gravity to try to merge these, because this would be very interesting. So we would add to the standard model of particle physics, add gravity as well. So this is very active research as well, but this is not where my research focuses on. My research is actually focusing on these quarks. We've seen them up and down quarks, which make protons and neutrons, and the strong force which keeps them together. And the question is like, okay, why am I interested in this particular force here? And before I come to that, maybe I give Kate a quick chance to explain the standard model as well, so you get another perspective of.
Our universe is ruled by 4 forces. You know gravity, which makes things attracted to each other if they have mass. But there are also 3 other forces. The strong nuclear force, that through strong interactions between the quarks binds the protons and neutrons together in the nucleus of the atom. The weak nuclear force, on the other hand, forces things apart and can, for instance, turn a neutron into a proton, an electron, and an antineutrino.
Oh dear, not nice.
And finally, there is the electromagnetic force, the one with the photons that account for light, electric potential, and magnetism, and keeps the atoms in place. The 4 forces affect the particles in totally different ways. Let's try an example with an electron and a neutron. Gravity only affects stuff which has mass, and as the electron is nearly massless, gravity only affects the electron a teeny tiny bit. The neutron, on the other hand, is quite heavy and is therefore more affected by gravity. Get it? The electromagnetic force doesn't care one bit about weight. The only thing it cares about is electric charge, so it will go after the electron and is totally cold towards a neutron. The weak and the strong nuclear forces are turned on by totally different things, flavor and color. In the so-called standard model, you will find the known elementary particles which can be combined into hundreds of more complicated particles. Not just neutrons and protons, but also some that are called pions, kaons, and eta C, and lambda, and all sorts of weird things. And they are all affected differently by the 4 forces. Crazy, right? So it's like when my mom texts me and I'm all like, whatever. But when Matt texts me, I'm just totally there. Oh, mom again. Ignore, Kate, ignore. Well, I'd better answer her. Thanks for watching. It was awesome.
Now we come back to the questions, okay, why did I choose the strong force to look into? And if you think about it, the understanding in the 1980s was very simple. We have a proton, there are 3 quarks in it, like we saw already, 2 up quarks, 1 down quark. But actually, if you look in detail and also look at the theory, it turns out actually it's much more complicated. Because the energies there are so high and fluctuations, quantum fluctuations are predominantly here, meaning at any given time, there's a lot of things popping out of the vacuum and disappearing all the time again. So it means things changed, our picture changed in order to thinking about this model and saying, okay, we'll have to deal with this whole mess in here. This is just a consequence of basically the simple theory which we can write down, which if you want to see, it's as a 1 line. And it's an incredibly simple theory, but it's very hard to solve. And furthermore, it explains, okay, 99% of the mass of the proton, or of us, of atoms, or of everything around us, actually comes from the strong nuclear force. The mass of the quarks are only a tiny bit. They're about a 1% issue relevant here. And this is why it's still the source of many unknowns and many uncertainties, especially if you think about these collider experiments. Whenever they do look at experiments, the most uncertainties they have is coming from the strong nuclear force to understand this. And what I do is I do computer simulations to solve this equation in a very worse way. I will explain this in a moment, to try to get a handle of these uncertainties and trying to explain quantities which we can compute on a simulation. Because the normal approach which physicists always take is like, well, we want to look at a special observable or some things we can experimentally measure, and then we expand these observables in terms of this long, we call it Taylor series, and we can also write this down in a pictographical way, which is then known as Fyman Diagrams, which you probably have heard and seen before. So, which means we expand this by making these diagrams more complicated and more complicated, which is shown on the right for me here. So I'm always adding something more and adding something more. Normally, the series would be, we stop the series at some point and say, okay, our accuracy is good enough because all the elements get smaller and smaller and smaller. But for the strong force, it turns out that this coefficient, which we expand in, so this alpha here, is of order 1. That means, okay, how many terms do we need in the series? All of them. We have to expand it to infinity, which is impossible, because we would have to compute infinitely many diagrams, which turns out to be not just a practical challenge, also a theoretical challenge. The alternative is to look at some other approach, and the other approach is known as the path integral formalism. And the idea is rather simple. We consider now to compute our observables via going from one point A to one point B. And weight this path by its action, or like how by the energy. And the only quite problem is like we have to take the integral over all possible paths we can ever imagine. So the shortest one, the longer one, going around, going to the moon and back, all of these paths have to be included. And if I write this down mathematically, this also ends up in a mathematically not well-defined integral, because I would have to take an infinite amount of integrals to solve this. And, well, then even we don't have to talk about convergence of these integrals, because we don't even know how to write this down formally correctly. One approach is, okay, instead of doing it like this over all possible paths, we can make a regularization. So we put it on a space-time grid, which we call the lattice. And the idea is, okay, we have this space-time grid in 4 dimensions. So here it's only shown in 2 dimensions, where we basically have a finite number of points between each space-time. And that means, okay, now we have these variables in between, and we can now consider all the possible paths from one point on this lattice to another point of this lattice. And this turns out to be now, instead of infinitely many integrals, it turns out to be only n, so a finite amount which we actually can handle. So this allows us, if we have a finite amount of integrals we need to solve, this is something we can do. Of course, these are still high-dimensional integrals, because even on this 2-dimensional example, we see there's a lot of lines we have to think about. And imagine we want to do not just 2 by 2 lattices, we want to, state-of-the-art these days is 128 times 64 to the 3. So there's a few more points, and if you think about now how is the dimensionality of this integral, it turns out to be roughly a billion-dimensional integral, which, of course, we cannot solve analytically or even want to try, so we do this numerically on a computer. And if you think about this, like if you go back to school mathematics and think about how did you integrals, like, okay, we take a triangular, do a trapezoidal rule, and trying this to estimate our integral like it's shown here on the left. Well, since we have a billion-dimensional integral, that means we take, say, 4 points in each dimension. That means we have to take 10 to the 600 million points. That will take longer than even the universe will live to compute this. So the idea is now, okay, we have to be more clever, and the idea is to do Monte Carlo. It's trying to effectively rolling dice, because the name Monte Carlo method goes back to the casinos in the city of Monte Carlo, and what they do, they're rolling dice in order to play games. Maybe as a quick example and show how it works, basically this is a numerical integration of, we want to have the area of the circle in a unit, so a box of 1 to 1, so the circle has radius 1, so we know the area of this curve is already the number pi, and this is something we want to compute. A simple idea, rolling dice, or like in this case, just throwing darts at this 2-dimensional problem. We count how many points are inside the circle and how many points are outside of the circle. And this is an approximation for pi. If you take this to n to infinity, then you get the correct answer. Of course, there's certain ways how you can improve this, but that's the basic idea of Monte Carlo simulation. Maybe show this in a slightly more better ways. There's, of course, various applets you can try, and if I just show this quickly. So the idea is the same. We have this circle, and let me just quickly start. So we throw 9 points. Unfortunately, probably cannot see them. There is red dots in the circle and blue dots out of the circle. And right now, we threw 11 points, 9 landed inside the circle and 11 out of total. So our approximation for pi right now is 3.27, which is not very accurate, but, well, let's throw more numbers. And you see, like, okay, the correct value we know is 3.1515 and so on. And this is the dashed line showing here. And we have now about 1,000 points thrown, and we get closer and closer. And of course, we have randomness in here, so meaning we will fluctuate around this, but we will approach this going more and more. And now you see the points actually filling up, because now we go to the 100,000s. And the simulation will soon go to stop at 1 million points, where we get very, very close to the actual number. You see, our final estimate, you can read, is 3.1413. It means we have 785,330 2 points landing inside the circle out of 1,000,000. This is the way Monte Carlo works in order to estimate the area now of pi. Of course, there's a few additional methods that improve this method, but the idea is mostly the same. Taking random numbers, in this case in 2 dimensions. Of course, in my problem, I have to have it in a 1 billion dimensional space, so I have to do it slightly more complicated. But a computer doesn't care. He can draw a billion numbers rather easily. Especially with these days of computing power, meaning computers can operate at 1 billion operations per second. So the whole thing, like what I'm looking at, is basically a lattice formulation of the strong force, which we also sometimes write as QCD, or quantum chromodynamics, the quantum theory of moving colors. And this is a natural field which basically, of course, the background is in particle physics, but it's a big field also in applied mathematics, and naturally also combines high performance computing, because we need to think about how to do billion dimensional integrals now. So until now I spent a lot of time talking about the strong force, and I hope that is what I convince you of what is the force we're looking at, but also the title had under extreme conditions, because life is not hard enough, so make it even more challenging by putting these under extreme conditions. And this is what we're after. This is an artist sketch of what we call the Qcd phase diagram. So of the strong force, how it behaves as we change temperature and how we change the density, or make it more compact. And we live in a universe where we have rather low temperature and, well, some non-zero density, because everything has some density. But we know in the early universe it was very compact and very hot, especially. So we started somewhere out here, and we slowly transitioned into the state where basically everything is now bound into protons, neutrons, so-called hadrons. But when you make it hot enough, they will start basically melting into what we call a Quark-Gluon Plasma, which is the orange area indicated here. Even though this is a diagram showing how we expect it to be, very little is actually known about this. That's why there is, like here, the statement critical endpoint and the question mark. There is a sketch where this line of transition happens. And we also know there is the densities where this transition typically appear would be the density of neutron stars. There's some speculation about if there's a color superconducting phase, even at higher densities. There might be even more states of matter which we don't know, which we haven't found yet. And the 2 lines shown here are 2 experiments, one in Germany, Darmstadt, and the other one in Switzerland and also in the US, trying to probe this with experiments, starting from where we are now, colliding atoms and trying to understand how this changes as a function of temperature. What I do as a theorist, trying to do computer simulations to understand this phase diagram as well. But maybe give you some overview what a phase diagram actually means, and probably go back to something which you're more familiar with, is the phase diagram of water. We know very well water freezes at 0 degrees and boils at 100 degrees at normal pressure. But of course, this changes if he changes the pressure or density. Then water freezes later or sooner, depending if it's more dense, or boils sooner or later. So normally we are here at 1 atmospheric pressure, meaning, okay, our freezing point is at 0 degrees, and it changes from ice to water, and then further on to vapor, to a gas state. In reality, actually, this phase diagram is slightly more complicated, but I can skip over the details here, that we have various different states of different ice structures, different ice formations and things. But the aim is here, like, okay, we're trying to have a simple picture, trying to make the analogy and trying to focus on things. So we focus on these transitions, going from one state to another state of matter. And also for water, there is a critical endpoint where basically at this point, at this temperature and density, we can't have this more. We also have something which we call triple point, at which all the 3 phases meet. So we have equal chance of going from ice to vapor, from vapor to water, and so on, which is an interesting problem. But again, we want to understand this for the strong force, for we have a similar structure. We know that basically, or we expect it to bend like this. We might have a critical endpoint here, where it changes from a smooth transition to a jumpy transition. And the question is like, okay, where are they located? How do they change? And what is its order? So when we looked at water, maybe I can quickly go back, we saw, okay, the relevant scale of here is temperatures in the range of 0 to 100 degrees Celsius. And densities of, say, 0 going to 200 atmospheres in pressure. So we have to think about the same problem if you think about the strong force and about what is the scale here for the transition. You see here the temperature is given in a unit which you're probably not familiar with, which is this MeV, mega electron volt. I can convert this into Kelvin or Celsius. This is roughly 10 to the 12 Kelvin. So this is a huge temperature. And I will explain in a moment how huge it is, comparing it to other phenomena. In terms of density, the density of neutron stars, so where we expect this transition to appear, is 10 to the 17 kilograms per cubic meter. Maybe just as a reference, also we'll show it in a second, 1,000 kilograms per cubic meter would be the density of water. So it's slightly more bigger. Maybe setting some scale, as I said, we use Kelvin, which is just the Celsius scale shifted by 270 degrees, so that we naturally end up that 0 Kelvin is absolute zero. So everything is standstill, nothing is moving, no interaction is happening. If you heat it up slowly, so at 1 millikelvin, helium-3, it's the melting point of helium-3. And if you think about this is a very, very low temperature. If you move further up, 2.7 Kelvin, so still minus 270 degrees Celsius, is what we find as the cosmic background radiation. They happen at 2.7 Kelvin. In this room, roughly we have 300 Kelvin, to 26 degrees, which is probably not exactly right, but give you an order of magnitude. We're talking here about order of magnitude, so I think this is probably the closest. Wood fire burns at 1,000 Kelvin, roughly. The surface of the sun is about at 10,000. The core temperature of the sun is at 1 million Kelvin. Supernovae happens at 10 billion degrees. And what we're talking about here, the melting point of hadrons, is at 10 to the 12, or a million times a million Kelvin. So you see it written out with zeros. And this is why I consider this extreme conditions, because it's very, very hot. Not to mention also, like when we talk about densities, like if you think the lowest we can imagine is probably interstellar medium, so basically sufficiently away from any stars and galaxies, the densities is typically 10 to the minus 19 kilograms per cubic meter, so it's effectively empty space. This is also what we think about interstellar space. As I mentioned already, water density is about 1,000 kilogram per cubic meter, and it turns out actually also our density is about the same, about 1,000 more or less. The Earth mean density is about 5,000, so just a factor 5 more dense than water or we are. The inner core itself is about a bit more, so 13,000 kilograms per cubic meter. And if you think about the elements, the most dense element we have is osmium, which is at 23,000 kilograms per cubic meter. If you go on, we need to think about more dense objects. Then we have to look at the core of the sun, which is 100,000, and supermassive black hole typically range of about 1 million, so 900,000 kilograms per cubic meter. Neutron stars are something that is amazingly dense, because you can see how many zeros we have. It's 10 to the 18, sometimes 10 to the 17 kilograms per cubic meter. Maybe give you some other reference scale of this. So like if you would take one small scoop out of the sun, that would be weighing about 2 kilograms, so 5 millimeters. If you would do that out of a neutron star, good luck lifting this of 5 billion kilograms, which would correspond to 900 times the Great Pyramid of Giza. So, and you imagine 5 milliliters, so this is a tiny amount. So meaning this is one of the most densest objects we actually can find in the universe. Of course, black holes make it even denser, but this is when other problems appear. So where does my research now fit into this? So what do I do on a daily basis? Like I try to get an idea of this Qcd phase diagram, which I have sketched here as well, showing, okay, we have temperature on one axis, density on the other axis, and we're now trying to explore how things change. So the easiest way we can do, we stick on the zero density, and we change the temperature. Increasing the temperature, and see how things change. And trying to understand, okay, at which point does the transition happen? And how does the transition happen? Of course, we can also do it slightly more. We can try to expand slowly into this diagram by going into higher densities. Last but not least, I'm currently doing something which is known as complex larger mass simulations, which is direct simulations of the QCD phase diagram in the whole range as possible. But the reason is why do we have to resort to a different method? It's called the Sine Problem, because as soon as we go away from this axis here of zero density, we have something which manifests. It's called the Sine Problem, and I will spend now a few minutes to explain what it means. And the Sine Problem happens in the path integral formalism as soon as we go into a non-zero density. And then this becomes a complex number, which unfortunately becomes very hard to integrate on. So what it means, instead of having something that behaves very nicely, we have something that oscillates very wildly. And this becomes more challenging because if we look at this is the integral we need to solve. Of course, it's still 1 billion dimensional, but now it has in addition also like this highly oscillatory factors, making it more challenging. And one big side effect is that our major technique, importance sampling Monte Carlo method, are not applicable anymore because they require a positive weight. And if it's oscillate, this is positive and negative. This also gives a reason why it's called the Sine Problem, because we have some positives and some negatives. Maybe to explain it a bit, because this is very specific for what I have to do, let's look at a simple one-dimensional integral. So 1 dimensions, we take just some envelope and we make it slightly complicated. We know we can solve this analytically very quickly, and we know the solution is square root of pi times e to the lambda squared divided by 4. Just as a reference, this is an integral we can solve, but this is how it looks. So let's choose the coefficient lambda to be 10, and then we find an integral that looks similar to the one we have to solve. And as you know, an integral is the area under the surface, so this is the, well, what is it, slightly green shaded area we need to compute, and it turns out this is 10 to the minus 11. So what we need to do, again, we want to do this numerically, we need to have contributions of order 1 that are positive, and we have contributions of order 1 that are negative, and we need to sum them up, and need to make sure that they sum up precisely enough that we get the leftover, which is supposed to be 10 to the minus 11. So this is relies on very, very precise cancellation, and is numerically very challenging. And this is the problem which we know as Sine Problem. And for QCD, or the strong force, this integral slightly looks a bit more complicated, but in principle it's the same manifestation. We have something which, for the experts, like this Fermi determinant, which causes the oscillation here, which is like shown here in red, the complex part of this integral. And this is where new methods are needed and actually developed. And one of them is known as the complex Legendre method, which I am using and actually also developing as well. But also I'm recently looking into the machine learning. Maybe we can use machine learning to train to compute these integrals a bit more efficiently in a different way. But just to give a heads up, what this complex Legendre method does is basically we take our values, which are just real numbers, change them into complex numbers. If you're not familiar with complex numbers, it doesn't matter, but this allows you to solve, for instance, the square root of -1. This is numbers that allows you to solve those. And then we use a stochastic method to evolve our equations of motion. And this is given by the Legendre equation, which is then just the stochastic differential equation which we need to solve and need to integrate. With this method, the Sine Problem can be circumvented. So this meaning we can avoid the Sine Problem altogether, but we have other small problems which we need to take in consideration. We need to consideration because we now are in the realm of complex analysis, we need to make sure that our integral actions and the observables we want to compute are actually all well-defined and, for the experts, holomorphic quantities. And also, because we want to simulate, in our case for the strong force, we need to simulate SU3. We need to make sure that our deviations from this SU3 actually are sufficiently under control in order to do our simulations. Otherwise, unfortunately, it turns up if you complexify the SU3, which is a compact group, into complexified degrees of freedom, you end up in an SL3C, which is a non-compact group. And then makes the integration out of a sudden slightly more complicated. And this is what is shown here. Like, if we take our normal degrees of freedom and add a slight imaginary part to it, we end up going from I would call it a very well-behaved mathematical group, SU3, to the special linear group in 3 dimensions over the complex numbers. Nevertheless, if you use the Lagrange method, you can derive an integration scheme that can solve this. So, for instance, in time like Euler scheme, but this is now stochastic differential equations. They also follow the E2 calculus, so our integration scheme has to be updated, has to be made more complicated. So this is what I spend most of the time, is trying to make this method work and trying to apply it to certain things. And this is what I've done in the past. Typically, this is results over the last year, trying to look into simulations at different temperatures. You see here the different colors indicate different temperatures. Again, in this unit of mega electron volt. And here I'm trying to probe from very hot, 200 MeV, which we expect to be above the transition, going to below, about 50 MeV, which is then below the transition. So we want to see how it changes. And this is one observable, which is the baryon density. So how dense in response to your function is. And this is a function of the density itself. And we trying to understand, okay, when this transition happens and how it happens. And each of these points is a computer simulations of not a billion dimensional integral. We reduced it to, say, a few millions, tens of millions integrals to make it slightly more feasible for a first step. But then this is a first indication, and also we're looking at this, and in order to trying to extract some information, okay, we see that the density above the critical temperature, so these are colors in red, suggestively indicated, show that the density remains 0, while as if you go below the transition, actually we see a behavior that inhabits some non-zero behavior. So we see actually we have crossed this transition by seeing that this number goes away from 0 to a non-zero value. The value itself here doesn't matter, but like just to see, okay, how we can find this transition in a very easiest way. And this is where my current research effort goes into, and trying to understand this and trying to improve this, because, well, we have to resign ourselves to, unfortunately, a scenario which is a bit unphysical. So we have to put our quarks to make slightly heavier to make the simulations run faster. But we can, this is a parameter we can tune. So in the next year or so, we'll go towards the actual physically relevant world. So right now we're looking at a world which would be if quarks would be heavier than they are. But this is something we can change in steps and trying to understand this as well. So right now, this is a prediction for this fictitious world, but like we can try to understand how it manifests itself already here. And we can learn something, how this would behave if we now change the quarks to a lighter scenario. And this is what my research is actually going on at the moment. And this is actually what I would like to end up on, not to go into too much depth, but I'm happy to take your questions.
So how are physicists confident that the same model will be valid in extreme conditions? For example, Newtonian physics, like in the everyday world, is valid, but when we go to extremes, it fails, right?
Yes.
So how do we know that the model is valid in the extreme conditions?
Well, the thing is, what we do first is like, well, we solve the currently best theory we have, like which is QCD, and trying to do this. And we do precision measurements. So we do precision physics computations, and we compare them to measurements, experimental measurements. And we try to match them up and see how good the agreement is. And this actually had led to the standard model of particle physics, because Newtonian physics has to be replaced by quantum mechanics eventually and has to be improved and improved. Right now, we know that the standard model is not complete. We know there is some things missing. We cannot, for instance, put gravity in it. We don't have any explanation of dark matter. The standard model of particle physics doesn't explain why there's more matter over antimatter, why we even exist. So these are things we know it's wrong. So there needs to be something wrong with it, but we need to find out where it is wrong. But right now, our computations and the experiments are agreeing to actually an impressive accuracy. Like Jörn was mentioning, my previous research was on the muon G-2. This is a quantity you can compute up to 9 decimal places. And the theoretical computations and the experiments agree to 9 decimal places. And people are looking into actually trying to increase it now because they know there should be something. It needs to show up. We call it new physics. Physics we can't put in and also which will be there because of the shortcomings of the standard model. But this is like ongoing research and trying to make precision. So we go on the precision front, trying to see, okay, does our theory prediction agree with the experiments? If they do, we believe the theory to be correct. But of course, if then at some point there's a discrepancy, we need to think about, okay, how do we need to improve our theory or how to improve our model to understand it? Right now, QCD is tested to an insane precision, which actually makes me believe right now we don't see, even though me as a physicist and also my colleagues want to see something wrong with it, because they want to have an explanation, why is this dark matter? Where is the asymmetry from antimatter and matter coming from? And other open questions in this area. The other front is, which is also done on the collider experiments, like trying to find new particles, which would be some massive manifestation of, which doesn't fit in the model, and trying to then need to improve our model, so it's always like a systematic way of trying to work with the experiment and trying to improving systematically. This is also what happened with Newton's theories. You start measuring planetary orbits and you realize actually they're slightly off. But then Einstein came along and said, okay, maybe this is not the correct description. You need to take the curvature of space-time into consideration. And then all of a sudden, they agree, the measurements, up to a level which is very precise, because now atomic clocks, we measure them and we can measure the curvature as well if you take an atomic clock on a plane, and you can measure like the discrepancy versus the one on Earth. But like this is how physicists are sure. It's a science, so we go away, we always take the experimental side and always compare it to the theories. And this is an iterative process which hasn't ended so far. And people always looking for failures because this would be exciting, because then something was overlooked. Like Einstein found out, okay, we overlooked the curvature. Planck or Bohr realized there is something wrong with, there needs to be quantum mechanics or quantum physics in there. And this is also how it led. And quantum physics was replaced by quantum field theory. So like this is like QCD is now one manifestation of a quantum field theory. That was a long answer for a short question.
More questions?
You mentioned that you're also looking at machine learning methods when evaluating these oscillating integrals.
Yes.
Could you say a little bit more about that? Because I've heard of works in using deep neural networks to evaluate or compute differential equations. Are you looking at similar type of research there?
Well, yeah, I can comment on this because we know this integral, like this one-dimensional problem, which is damn easy, but if you make a transformation from x going to slightly into the complex plane, this oscillation becomes milder and more controllable. So maybe a change of variables is the way to go forward. But the problem in a 1 billion dimensional way to write a change of variables, which one to find, is another problem by itself. And this is where my colleagues and myself think about, okay, maybe machine learning can find a transformation from x going to z that would actually make this oscillation less severe, let's put it this way. And this is where, so it's more like finding a variable transformation, which is actually trying to help. But other colleagues I know, they're trying to think about this problem and trying to integrate. My approach is basically integrating a stochastic differential equation, but the normal method is like, okay, you integrate like this integral with Monte Carlo methods. But for integral methods to work sufficiently well, you need to have a positive weight. With oscillating, you have some parts which are negative, so you always will be screwed. But they found a way basically with machine learning also, like there is a way to transform this into a purely positive way. But then it's again a variable transformation rather than a integration of a partial or stochastic differential equation. And you can think about like in this terms, like if you one-dimensional integral, you change x to x plus some small imaginary part, and then the dampening goes down quite significant, but there is an optimal solution where actually the damping completely disappears. But the problem is to find this. I can, of course, in one dimension, I can write it down quite easily, but in more or say billion dimensions, it becomes especially more tricky, considering I also want to do numerically simulations with this. But machine learning can help, and especially has shown that helps significantly to go into a phase where maybe it's not completely real, but the error we make by ignoring the oscillating part is so small that we can control it. This is something to be looked at. And this is what at least people hope, and this is why my machine learning is something coming up these days, looking into this, because that would be another approach complementary to this approach with stochastic differential equations. Hope that makes sense.
Maybe I can ask a question as well. So,
sure.
We saw the simulation of pi in the beginning.
Yep.
And what we see is that the convergence is rather slow with this Monte Carlo simulation. Of course, we have much better approximations to pi that are much faster.
Yes.
But it raises the sort of fundamental question. When you're doing your lattice gauge theory,
yep,
how do you understand how much is off? Because, you know, it could be that when you're doing these simulations and so on, you are way off from sort of the true answer of this theory here. And, you know, how do you deal with that? And in particular also with the complex Langevin equation, I mean, you will have some problems understanding how well are your approximations. So do you have error estimates?
Yes. This is also very crucial that there is error estimates, but you rely heavily on statistics in this case, in this framework. And also
but are your simulations within the bounds of those error estimates? I mean, those error estimates must be quite large when you're doing Monte Carlo simulations, such multi-dimensional spaces.
It actually, like, well, Monte Carlo is the, let's go back quickly. I mentioned quickly at some point, actually you have to go forward. No, actually, I'm lost in my own talk. Let's scroll like this. Of course, Monte Carlo method is like the one example which I can explain the best. What we really do is importance sampling. So we're trying to approximate this in a significant better way. And even with the standard Monte Carlo, you can estimate what your uncertainties are, variances are.
In that case, yes, obviously.
In that case.
Yeah.
Well, the importance sampling is just, instead of using, because what is lost? There's a lot of empty space which we know is not relevant to us, because we need to, how would you improve this Monte Carlo estimate? Well, we would have some approximation and we would draw random numbers distributed according to roughly the circle or some approximation of a circle. And that would, it's just a transformation of our procedure, but the underlying statistics or like the, law of large numbers still holds. So like the variance is still controllable. But this is a method basically based on the Monte Carlo method, trying to reduce the variance of it. But you still have the estimate of the variance, and it is always crucial to keep this variance under control and understand it. And this is what when I showed my results, there's always error bars on this, which is typically estimated giving the variance of the simulation on 1,000 up to, 100,000 samples. But of course, this is an error we have, and because we draw a finite amount of random numbers, we always will have. But you can improve it. You can just draw more random numbers and make it more precise, or find a better algorithm that make the variance smaller.
And then, of course, there's a problem also. We don't know if this converges when you move the lattice size down, right?
Well, we know basically we discretize it, and then this is an approximation which you can formally make and can expand in this lattice spacing. So we know the expected behavior. The one thing we are not sure about is like, okay, are you in the right scaling regime? But this is why you have to scan a lot of different scales in order to see that you're actually in the right scaling regime. And the lattice approach basically has a few unsystematic. So like we have the lattice spacing, the minimum distance, and also we have a finite box because we can't simulate infinitely large boxes. And well, what we can study, we know how the continuum theory relates to the lattice theory. There is a big branch, also like mathematicians working on it, how this is related and how this converges.
But they are conjecturally right to a large extent because we don't know the exact definition, as you have pointed out at the beginning. Right. Okay, but yeah.
But you look at if you're the right scaling regime of your expected behavior, and then you can do an extrapolation to zero lattice spacing. Of course, my results here, they're at a fixed lattice spacing at a fixed box, so they still have systematic errors which are not shown. But this is something we can improve. We can do 3 different lattice spacing, 3 different volumes, and then this is the bare minimum to extrapolate then to zero lattice spacing and to infinite volume. Of course, ideally we want more, but this always is a compromise between effort and gain. But the thing is, like, I think it's a systematically improvable approach. This is, I think, the important message here. That you basically, you can take the numbers of n going to infinity for the Monte Carlo method, we can take the lattice spacing smaller, we can take the boxes larger. And these are the theory, we understand how the theory changes as a function of all of these 3 variables, so we can understand how the behavior should be. Of course, we need to be sure that we're in the right scaling regime, otherwise, well, you can try to extrapolate something very far away, then of course this will be wrong. But if you make it sufficiently small, we know the scales of our theory. And we'd be very lucky that the scales do match up so we can do simulation in this regime. Because imagine we want to have a tiny particle and then we simulate something, okay, very heavy, which would require the lattice of not 100 points, which 1,000,000 points. And then 1,000,000 4-dimensional, even with these days, with the computers these days, don't even bother.
Right.
But
okay.
But I think hopefully that answers your question.
Yeah, no, that's fine. So another question here.
So this is probably a totally ignorant question from somebody who can't remember any physics from high school anymore. But I mean, there is the second law of thermodynamics. Does that apply in the nucleus?
Well, certainly.
So that would work towards more entropy.
Well, the universe is always going towards more, higher entropy. Yes.
So with your increasing temperatures in your model, your extreme conditions, how would that, is that accounted for?
Well, we simulate in for a fixed entropy, or like a fixed entropy. Well, but in a way, if you think about let's go to the back at the beginning for the QCD phase diagram. You're asking, okay, but entropy. So like when we think about our current universe, like things are in hadrons, this is a more ordered state than if you make it hotter. Because there everything is walking free, so like the entropy would be actually larger. But this is the thing, there's one thing which you can spend energy to reduce your entropy. And this is what has been done here. Like energy has been spent because cooling down is energetically favorable to make it more organized. But then, of course, if you take the opposite approach, like we're making it hotter and hotter, we actually get a more chaotic and state with a higher entropy. But we take it into consideration, but it applies here as well. Like we go from an ordered state to a more disorganized state, which is entropic, has a larger entropy. But of course, to speak about, this is like, thermodynamics, so entropy is a very important quantity in thermodynamics, and it's an essential guiding thing there.
So does the nucleus become bigger? Or I'm just trying to get my head around what's happening.
This is what we're trying to understand, like how it would change. But like I wouldn't expect it to be bigger because it's bound. This is how the forces. Like now, it's basically the size is determined by the forces, like how it's in a stable situation, like something pulling in, something pulling out, like. And you imagine, okay, well, we see gravity. That would explain it should be attracting. Electromagnetic forces, the electron should be attracted as well. But then in the middle, we have quarks, which are positively charged, some of them. So we have two quarks, which are very, very close to each other and positively charged. So they have a strong force repelling electromagnetic, but the strong force is keeping them in bound. So it's like a stable between that. But if you change the temperature, we change the forces, or we believe so, and then of course things will change. And if you think about the thermodynamic system, we need typically three quantities. We need like the entropy, the temperature, and the particle number or density, depending on which setup you take to describe the system fully. So the entropy is one of them. But the dual one of the entropy is actually, I'm not sure if you remember that, but the dual one is like a temperature on this.
Yeah.
So
that was also just a warm up for my second question, which is I once read that what everybody thought it was a book about ideas that must die. I know I've talked about it previously, but there were a lot of people saying that the second law of thermodynamics had to die because it was actually not always true and it was blocking progress in the field. So I want to challenge you here because you know all of you that Nina and I are organizing this day on the 21st of September where we will have people come and present a dogma that's blocking progress in their field so we can, or at least a dogma which is a dogma and nobody actually really can prove, so we can all discuss the dogmas unbiasedly within our field. So I want to challenge you to hear which dogma in your field that you might come and talk about on the 21st of September.
That's a good question. But I think I would not give up the second law of thermodynamics because there is a lot of evidence for it working. Like, of course, you have to always consider like the second law of thermodynamics only holds in a closed system. So when do you have a closed system? And typically, if you think about most when it's violated, it's actually not the closed system where you can have either particles coming in or energy coming in from the outside. Because this is the way you can violate it.
Another way to sort of answer this question is that I think a lot of physics has to do with just killing dogmas all the time.
Yes.
Because the reason why people
Newton mechanics, the example was earlier.
Yeah, half of the time, I mean, most of the time, you are verifying the laws as they are, like Newton's law. For many centuries, it was just verified. And then people started seeing it's failing.
And then it's been actually like...
And then quantum mechanics arose, right?
And quantum mechanics...
that also had some problems. I mean, there were serious people who were saying, no, this is ridiculous. There is no quantum mechanics. And there is this famous conference at Solar Wave Conference in 1927 where somehow it was conceived, okay, no, there is quantum mechanics. But I think this is a constant thing in physics. As physics is progressing, you heard, new physics. We're looking for new physics. So the moment I would maybe even dare to say most of the sort of theoretical high end is looking for dogmas to fail.
I'm happy to give up. As one particle is found which violates all of this, I'm happy to give it up, but then you need to explain, okay, why was this theory so correct until now? Where is the limit? So this is also what I said with the example with Newton mechanics. Like for the body movements, Newton mechanics also for our daily life, Newton mechanics works exceptionally well. But then Einstein came around and said, okay, it actually is different. We can actually, it has to be described correctly, but people there is to this day, people who don't believe it or like can't see it, say like, no, I can take Newton mechanics, it explains everything. But if you look in detail, actually it's not correct. It's an approximation going to very large scales or very many particles. Because quantum mechanics becomes relevant if you think about very small scales or energies. And then things become weird because you can't think about, okay, a particle, is it at one space or you can't even put the position or the momentum down to a certain level, which is something to give up. We cannot measure, this is Heisenberg's uncertainty principle, measure a particle's position and space up to a certain accuracy. And this led to the whole Newtonian physics where you think, okay, as soon as I know the state of the universe, I can compute it exactly, arbitrarily precise? Yes. But then quantum mechanics came around and said, okay, no, you cannot. Discussion over.
So you're actually claiming that physicists are the only ones who don't really
No.
are bound by dogmas.
No.
No. We, of course, also, we stick to our theories and we evolve of them, but I think we want to find new ones. And this would be, they always keep saying it was life-changing event. Say, okay, new particles discovered, this makes new physics relevant. Like, okay, there needs to be a fifth force now. We don't know. We wish there were one. There needs to be some way how dark energy is in the picture as well.
And on top of this, you can add that if we're talking about Newton's law, that's completely on mathematical firm ground. If we talk about quantum mechanics, completely on mathematical firm ground. But my questions was a bit directed at, if you look at what Benjamin is studying, this is not on mathematical firm ground. In fact, we can prove that some of these path integrals you were showing us before don't exist mathematically.
Well, I claim the same. The path integral over space doesn't exist, but if we regularize it on a lattice, actually is well defined
Yeah, but what
mathematically.
about then if you change the lattice? What theorems are there that shows it's independent of the lattice?
Yes.
Well, there are none.
But you can also make the more dogmatic approach, saying, okay, we live in a lattice world where we have a finite amount.
Okay.
But we
Are
don't
there
have a
more
continuous problem.
No. Okay, let's thank Benjamin again for this very wonderful talk.